I said within the last lecture that I would delay it till 5:45 because some people have classes till 6. So that will stand. We will have that on Thursday the 13th. The next thing to do is you want the help session to say 5:30 on the Wednesday, that's the day before, or on the Friday, whatever you like. So just a minute, I can't judge by methods the preference of the audience. Let's have a show of hands for the Wednesday. Let's have a show of hands for the Friday. Okay, Friday it is.
Okay, I can go to that now.
I will, that's actually more convenient because I think the chance of getting this room on the Friday is much greater. There appears to be some sort of passing
So
here
5:45?
on Wednesday. So I will deal with that and I'll make so this coming Wednesday I gather that nobody will be here on Monday. So I'll be lecturing to an empty room. Okay, so on the Wednesday lecture I will finalize everything and confirm that this is the room. But for the Thursday I have this room and it is at 5:45. Okay, now what I have to do, I have to move on quickly, is to continue talking about aromatic electrophilic substitution. And right at the end of the last lecture, tell you that if you treat benzene with bromine and the catalytic amount of ferric bromide, what you get is bromobenzene. And what I need to do, and that is just one example of this whole class of reactions called electrophilic aromatic substitution. It's called aromatic substitution because you're dealing with aromatic compounds, of which benzene is the most famous prototype, started by Michael Faraday. Very great British physicist, I suppose. I visited his laboratories in London. They're very, very nice. There's something even nicer about them. Right opposite the laboratories is a very exclusive hotel called Brown's Hotel. You can have the most wonderful afternoon tea. You can even bring a suitcase full of money. My mother likes me to take her there. That's the only reason why she put up with visiting Faraday museums. Okay, this is one of the methods, one of the examples of electrophilic aromatic substitution. It's a bromination. You can do the same thing with chlorination, in which case you use ferric chloride. Now, the next type of electrophilic aromatic substitution is something called nitration. And what you do is you take benzene, and remember I'm always just writing down one resonance structure. If I happen to write this one, there's no difference from if I write the other resonance structure. I just happen to write whatever I fancy. What you do is you take a mixture of concentrated nitric acid and concentrated sulfuric acid, and what you get is a substance called nitrobenzene. Now, what's the mechanism? I told you the mechanism of electrophilic aromatic bromination, and I told you the mechanism of electrophilic aromatic chlorination is exactly the same, except bromine. What's the mechanism of electrophilic aromatic nitration? Well, the mechanism is that you take nitric acid, this is the formula of nitric acid, and the sulfuric acid, protonates the nitric acid so that you get two substances formed, two species formed. This one, and that protonated nitric acid. And once this oxygen on nitric acid has been protonated, water can be expelled, and you get a new species, which has got a special name. It is called the nitroniumide. Can you guys at the back see this? Yes?
Yeah.
Good. Does anybody want to say no? If they do, feel free. Because I can write bigger, or I don't know what I can do. I can break this open so it's quicker. This is the actual nitrating species. Now, let me show you how that works. This is positively charged. Obviously, it's electrophilic. And so it will be attacked. One of my students many years ago put it, the electrons leap out. And now, some nucleophile, which is either that or water, regenerates the aromatic ring by capturing this proton, and the electrons here move into this region so that the system becomes aromatic again. And by saying that it becomes aromatic again, I mean that it has now 6 electrons delocalized over the perimeter of the regular hexagon that constitutes the framework of benzene. And so you can see that this aromatic nitration is just one example of the general pattern where the electrophilic species that you can represent as E plus is attacked by electrons in the benzene ring to give you a carbocation, which is resonance stabilized. I can move the electrons here, put a plus charge there, or I can move these around there, put a plus charge there. So I can write some resonance structures, but it is not as resonance stabilized as benzene itself. So this is just an example where E plus happens to be NO2 plus. And then in every case, this resonance stabilized species rearomatizes by having some nucleophile that's present in the mixture. You've got that anion derived from sulfuric acid. You've also got water with its lone pair. One or other or both of those will then attack this proton, and the electrons can then move into a position in which the aromaticity of the benzene ring is restored. So it follows exactly the same pattern as aromatization and fluorination. Just get something E plus, E going to be NO2 plus here. It's attacked by the benzene ring. Now, as I told you in the last lecture, there's about half a dozen of standard electrophilic aromatic substitution reactions. There's fluorination and bromination, there's nitration, there's sulfonation, in which you put an SO3 group on the ring, there's alkylation, in which you put an alkyl group on the ring, and there's acylation, in which you put an acyl group on the ring. So we've done bromination and nitration. I want to do now sulfonation. And you'll see it follows exactly the same pattern.
this one.
Very interesting story. I decided to school like early and spend 2 hours because then he would drop me off because he was at school today. And then it turns out he's running late, so he's going to get his motorbike and sent together with his dad into the shop. So, okay, I'm a little late. I'm a bit late for my first hour. I got to Bonnie for shit. I got my duffel bag at the train station.
Oh.
Get back. So I get back to make sure I grab my duffel bag and the bus stop because I was back here. So I totally missed it.
Oh, it's okay. No wonder. Because we were like, you weren't in bio, so we weren't sure if you were coming today.
Yeah, I totally get it.
Okay.
Never.
You made it.
Interesting morning. Got a picture last night.
This compound is called benzene sulfonic acid, and you can see that it arises by attack of the electrons in the benzene ring on SO3. And the way that that actually occurs concentrated sulfuric acid. Concentrated sulfuric acid provides a source of SO3. And the SO3 attacked in the usual way by electrons in the benzene ring. And now this negative entity comes along and re-aromatizes benzene ring. Now, there is one difference between sulfonation and nitration, and the difference is that all the steps are reversible. And that means that if you start off with benzene sulfonic acid and you want to liberate benzene, what you do is you heat the benzene sulfonic acid with water. If, however, you want to go in the other direction and go from benzene to benzene sulfonic acid, then you must have very little water present. And so you use concentrated sulfuric acid. Or, better still, you use fuming sulfuric acid. And all that fuming sulfuric acid is concentrated sulfuric acid into which you have bubbled sulfur trioxide. When you take sulfur off, like fuse come out, it's sulfur trioxide. So the case of sulfonation has got a little bit of a different twist to it than electrophilic aromatic bromination, chlorination, and nitration. And this twist is that the steps in the sulfonation process are reversible. So normally one uses fuming sulfuric acid, very, very concentrated sulfuric acid, best of all, fuming sulfuric acid, and in fact, the tank that is virtually no water there and below the sulfur trioxide drives the equilibrium over to the right, so you get sulfonation. On the other hand, if you have a sulfonic acid, an SO3 group attached want to remove it, all you do is you heat the compound with water. And then the step will go backwards. So you'll end up with dilute sulfuric acid, which doesn't really sulfonate benzene, and you'll end up also with benzene. So that's the story for sulfonation. Now we come to a rather more complicated story. I've done the method of attaching the bromine or chloride to the ring, the benzene ring. I've done the method for attaching a nitro group to the benzene ring. I've just done the method for attaching an SO3 group to a benzene ring, and also for aluminum such a group. Now I want to tell you about I brought my cell phone for a very good reason. I don't like cell phones, and it's extremely rude when people in an audience use them and switch them on and so forth and so on. In the last lecture, of course, there was some criminal who messed up the blackboard. And so before coming here, I got a number of the technical people who can help. And I must admit, I forgot to switch this off. That's why it rang. And why I didn't know what it was. There are only 2 people in the world who have my number. Supposed to only be 2 people. My mother, who's nearly 95, and my brother. And so any other number in the wrong number. Anyway, it's quite late at night. It's not there. So this is why I brought it.
Oh, Georgia said he's not
Okay, what I want to do now is to talk about this more complicated business of testing an alkyl. And that's called Friedel-Crafts alkylation.
Friedel-Crafts alkylation. Now we're learning Friedel-Crafts alkylation. Have you finished your postdoc? Did you do your piece that you were using like the mold and stuff? Like limiting age in the class? We'll see what I get. I'm not sure yet. It was like between 102 and 105. Then I don't have theology until after.
In the presence of aluminium trichloride, what happens is that the alkyl group becomes attached to the benzene ring. In other words, one of the hydrogens on the benzene ring is replaced, it's substituted by an alkyl group. And so overall, this is just the same as electrolytic aromatic chlorination, or bromination, or nitration, or sulfonation, because in every one of those cases, you are replacing one of the aromatic hydrogens, one of the hydrogens on the benzene ring, by some other group. In this case, it happens to be an alkyl group. So this reaction is a little more complicated. So let me first tell you, by means of an example, exactly what is going on. So supposing that our alkyl chloride is 2-chloropropane, or isopropyl chloride. If you treat that with aluminium trichloride, you get that process occurring, because what happens is the lone pairs go there. And then that breaks. And so that gives you those two species. And now this is captured by the benzene. Then the system de-aromatizes. Now, I said a moment ago that this is a little more complicated than the others, and I'll now tell you the reason, or some of the reasons. One of them is that the nature of the alkyl halide has a big influence on what's going on. If you have a secondary alkyl halide, for example, probably you get a carbocation like I have written. However, if you use a primary alkyl halide, as you know, primary carbocations are not very easy to make. They're not stable species. They're high energy. So probably the mechanism is a little bit different. Let me point out something reasonable to represent the mechanism for a primary alkyl halide. In the case of a primary alkyl halide, you probably get a complex, so it doesn't break up to the actual carbocation. And that happens. So in the case of a primary alkyl halide, perhaps you don't get the discrete carbocation. You get something that behaves like a carbocation, but it's not as fully a positive charge on carbon as in the case of a secondary alkyl halide. Then there's another complication, quite a serious complication with the primary alkyl halide. Supposing that this is my primary alkyl halide, and supposing that I just write it, I'll put it in inverted commas, as a carbocation. I'm just writing it as carbocation that makes it easier to understand. This carbocation, as I told you, it's a primary carbocation, it's not as stable as secondary carbocation. So what it does is it undergoes a migration to give now a secondary carbocation. So if you try and do a Figure-Crafts alkylation with a primary halide, you will get some of the straight chain carbon unit attached to your benzene ring, but you're also very likely to get the Figure-Crafts alkylation that results from rearrangement of the primary carbocation to a secondary carbocation. In other words, you'll get a mixture. And the mixture comes about because the primary carbocation or its synthetic equivalent actually undergoes rearrangement to a much more stable secondary carbocation. And so there are problems with the Figure-Crafts alkylation, and I mentioned now this particular problem. There is another problem, and the other problem is that the product of a Figure-Crafts alkylation is reactive towards alkylation than the starting material. So if you start with benzene and you carry out a Clive alkylation, you get one alkyl group onto the molecule, but that product now reacts even quicker with the alkylating acid. So you get what's called polyalkylation, which just is a fancy word that means that you're sticking more than one alkyl group on the benzene ring. So once again, you get a mixture. So those are the bad things about the Clive alkylation, but there are some good things about it, and one of them is that it is not limited to alkyl halides. You see, if you look at the mechanism that I put on the board, you will see that the essential details of the mechanism are that somehow you generate a carbocation. And the carbocation, positively charged carbon, is then attacked by the electron with the benzene ring. Well, because that isn't the case, it actually doesn't matter how you get the carbocation. You generate from an alkyl halide. And I could ask some fairy, give me a carbocation. Fairy gives you carbocation, you put it in benzene and it reacts. But you can make the carbocation in all sorts of ways. So I'll show you a few other ways of generating the carbocation.
Awesome. Yeah, I thought I talked about this before. Very. You should probably go in for something.
If you treat propylene with a strong acid, you know that what will happen is you'll generate that carbocation. Which you did this all in Chem 261. So this carbocation then reacts with the benzene to give you isopropyl benzene. You also know, for example, well, let me just write it up, then I'll tell you what you actually know. You know that if you take cyclohexene and protonate it, you will get, see a proton is picked up, so you get this. And this is attacked by benzene to give you now cyclohexyl benzene. And equally, you know that if you take cyclohexyl alcohol and treat it with a Lewis acid, you will generate carbocation by this process. And if you put this, if you do this in benzene, by the general mechanism that I've given you so far, the carbocation will be captured. So, although I told you that there are some disadvantages to the Clive alkylation, it's not all doom and gloom. There are some aspects of it that are very, very valuable. That's why it's a named reaction. In other words, it's named after somebody, after two people, Charles Friedel and There are some advantages to it, but there are disadvantages. And one of the disadvantages is that if you have a primary carbocation, in fact, it might rearrange before it reacts with the benzene, and therefore you will not stick on the alkyl group that you thought you would stick on to the benzene ring. And the other disadvantage, and this is actually a more serious disadvantage, is that once you stuck one alkyl group on the benzene ring, the resulting product is more reactive. There are ways of combating that if the starting materials are cheap. That is a problem. We now come on to the Friedel-Crafts acylation. So far I've told you how to replace an aromatic hydrogen by chlorine or bromine, or by a nitro group, or by an SO3H group, and that process is reversible, and also how to replace one of the aromatic hydrogens by an alkyl group, most frequently a secondary alkyl group, because the second carbocation is stable. Now I want to tell you about the Friedel-Crafts acylation.
You're so sick. Like how when your neck is kind of like holding your head up. Your poor jacket. No, you rub it against your enemy. Rub it against your enemies. Is that okay?
This is an example of Friedel-Crafts acylation. Clearly what we've done here, as we have done in all the other examples of the electrophilic aromatic substitution, we have replaced one of the aromatic hydrogens by some other group. In this case, it happens to be an acyl group, and an acyl group is a carbonyl carrying a carbon. So this could be ethyl, propyl, butyl, cyclohexyl, or even a benzene ring. Carbonyl carrying a carbon is an acyl group. So the question is a little bit different from the others. In this case, you use a stoichiometric amount of aluminium, at least one equivalent of the Lewis acid, such as aluminium trichloride. Now, I want to give you a couple of examples, but before I do that, I want to tell you that you don't need to use an acid chloride. This is that compound is called an acid chloride. This one is called an anhydride. An acid anhydride. You can also use an acid anhydride, but if you do, you get two products. What you want, same as before, plus half of the acid anhydride, so it's less economical. Now the question is, again, how do these things work? What's actually going on? Well, from everything I've told you so far, I'm sure you'll be able to guess that you make some electrophilic species, some positively charged species, and then the electrons on the benzene ring can, as I said before, leap out and attack that positively charged species to generate a resonance stabilized carbocation. that then can be rearomatized by loss of a proton. I'm sure you all realize that that's what's going on, but you don't know the details. So let me show you now the details. Let's do the details for the acid chloride. So what happens is you form something called an acylium ion. And an acylium ion, I use two different ways. I'll write the other resonance structure. Is just that. Now, once you've got the acylium ion, it can be attacked by the benzene ring, and then there's loss of a proton, and so you attach the acyl group to the benzene ring. Now I said you use one equivalent of aluminium trichloride, and the reason is that this product actually complexes with aluminium trichloride. And so the product removes aluminium trichloride from the system. And therefore you need a whole equivalent of aluminium trichloride. If the product did not remove aluminium trichloride from the system, all you need is a catalytic amount, because at the end of the acylation, the aluminium trichloride will be released. It is released, but unfortunately it's gobbled up by the product. And so you need one equivalent of aluminium trichloride, whereas in other reactions that I've talked about, you only need catalytic amounts of a reaction. So there are some differences. There's another difference, which is one of the very best virtues of Friedel-Crafts acylation. And that difference is that the product of a Friedel-Crafts acylation is less reactive to the acylation agent than the starting material. And that means that you do not get polyacylation. One acyl group goes on, and that stuff is less reactive than the starting benzene. And so the reaction stops there. So unlike Friedel-Crafts alkylation, where you do get polysubstitution, in Friedel-Crafts acylation you don't. Now, when you have an anhydride, there's a write up the mechanism for the anhydride.
Would have been nice to know the differences. So for mine, I just wrote like the products.
so you need more than one equivalent. You need two equivalents of aluminium trichloride when you do the Peter-Craft acylation. And when you pour this into water, this breaks, the bond between oxygen and aluminium breaks, and you release the ketone that you've got. Now, I haven't emphasized, well, I emphasized it slightly, maybe not enough. In the Peter-Craft alkylation, one of the dangers is polyalkylation. In the Peter-Craft acylation, you don't have that danger. Now, it frequently occurs that you want to attach to a benzene ring one alkyl group and only one alkyl group. And it also frequently occurs that if you try to do that, you get polyalkylation. How can you get around that? You can get around that very, very nicely. Because if you take a product of Friedel-Craft's acylation and you treat it with zinc in a strong acid, with zinc in a strong acid, you replace the oxygen of the carbonyl by two hydrogens. So this product that I've written here is the same as you would get from a Friedel-Craft alkylation if it worked perfectly and you didn't get polyalkylation. This is the point I'm trying to make. If a particular Friedel-Craft alkylation gives you what you want contaminated by the products of polyalkylation, what you do instead is you use the Friedel-Craft acylation, which goes very cleanly, and then you remove the carbonyl oxygen by replacing it by hydrogen. And that you do by what is called the Clemmensen reduction. The Clemmensen reduction just involves taking the ketone and boiling it up in acid with zinc. The mechanism that's quite complicated. We won't go into it. Emerson was a Danish chemist. There is one other problem with Friedel-Craft reactions, and that is that if you have a very strongly electron withdrawing group of the benzene ring, these reactions don't go. Which is sort of reasonable, because what's happening is electrons are coming out of the ring to attack a positively charged species. And if you've got electron withdrawing groups already on the ring, clearly they would make it less likely that electrons in the ring can jump out and attack something else. And so there are some limitations for the Friedel-Craft reaction.